Welcome to the deep dive. Today we're plunging into a topic right at the cutting edge of large language model, or LLM, development. It's all about how to make these incredible AI powerhouses smarter and faster, especially when dealing with, really long conversations or documents. You know those moments when an LLM seems to forget something you told it 20 pages ago? Well, a lot of that comes down to a fundamental memory challenge.
Yeah, and what's truly fascinating here, I think, is that the memory bottleneck in LLMs, specifically something called the key value or KV cache, it's a major hurdle. It really limits how widely these models can be deployed, especially for complex long-form tasks or, say, on devices with less memory. It's actually one of the biggest roadblocks to scaling them up to handle truly long contexts.
Right. And our mission today is to explore a fascinating new approach called Fourier-Attention. It's detailed in this paper, Beyond Homogeneous Attention, memory-efficient LLMs via Fourier-Approximated KV cache. And this isn't just another small tweak, apparently. It offers a training-free way to tackle this memory problem. And it comes with some truly surprising findings about how LLMs actually think about information, you could say. You're going to hear about innovative techniques and some pretty impressive results on real-world benchmarks that really push the boundaries of what these models can do. So to begin, let's maybe break down this KV cache. What exactly is it, and why does it become such a memory hog for LLMs?
Okay, yeah. So imagine the LLM has a kind of mental scratch pad, right? That's its key value cache or KV cache. It basically scribbles down important notes about every word or token it's seen or generated so far. Now, when an LLM generates text one token at a time, that process is called autoregressive decoding, it needs to remember the context that came before. So the KV cache stores these pre-computed key and value vectors from all those previous tokens. This avoids having the model recompute them for every single new word, which would be incredibly inefficient.
Okay, so it's a speed thing, but the problem is the size.
Exactly. The problem is that this scratch pad just grows linearly with the length of the text. The longer the context, the more memory the KV cache demands. Yeah. And it quickly becomes a significant bottleneck, especially, like I said, for deploying LLMs in environments with limited resources. You just run out of memory.
Right. The longer the text, the more memory it eats up. That's a very clear scaling challenge. So what specific approaches have researchers tried to get around this? And I guess where have they fallen short?
That's a really good question. Because people have definitely tried things. Prior research has explored several avenues to manage this memory issue. One pretty common approach involves what are called token eviction strategies. You see these in things like streaming LLM or SnapKV. You could think of these like a selective memory purge. They prune or discard parts of the sequence, often based on, say, how much attention the model paid to them, or maybe just their position in the text.
But there's a catch.
Yeah, the core limitation is that they tend to treat all the internal head dimensions within the transformer architecture kind of uniformly, homogeneously. They don't really differentiate the different parts of the data, or maybe different dimensions within the model's representation, might have varying levels of importance for the overall context. It's a bit blunt.
Okay, so that's eviction. What else?
Well, another method is quantization. This is used in techniques like KIVI or KV-Quant. This is kind of like compressing a large image file by using fewer colors. It reduces memory by using fewer bits to represent the data. And while it's effective in saving space, this often comes at the cost of compromising the model's accuracy. You lose some fidelity.
Right, a classic trade-off.
Precisely. And lastly, there's hidden dimension compression, like a method called PALU. This also applies uniform compression ratios across all dimensions. So the fundamental flaw, really, across most of these existing methods is their assumption of homogeneous or uniform treatment of these transformer head dimensions. They generally fail to dynamically allocate resources based on the actual importance of these dimensions. Plus, some of those attention-guided strategies can introduce their own memory and latency overheads because they need to keep recalculating attention scores, which is something Fourier-Attention specifically tries to avoid.
Okay, so if these existing methods mostly miss the mark by treating everything uniformly, what's Fourier-Attention's big idea then? How does it fundamentally rethink this whole problem?
This is where it gets really interesting. What truly sets Fourier-Attention apart isn't just, say, a new compression algorithm, but actually a groundbreaking discovery about how LLMs fundamentally process information. The core insight of this paper is what they call the bifurcation of transformer head dimensions. It sounds technical, but basically the researchers kind of cracked open the black box and found something pretty astonishing. A split in how different parts of the model's memory actually work.
A split, okay.
Yeah, it reveals that lower and upper dimensions have distinct and crucial roles in how the model processes information. They found that, well, not all dimensions are created equal.
Huh. That's a really profound revelation, actually. Can you elaborate on these distinct roles? What did the researchers observe in this bifurcation?
Absolutely. So they observed that the lower dimensions, and specifically they looked at LLaMA models, finding it was roughly the first 70 dimensions. These primarily focus on local context. Think of them as handling the immediate conversation, paying sharp attention to just the most recent tokens, the stuff that just happened.
Okay, the nearby words.
Exactly. In contrast, the upper dimensions, which in their case were the latter 58 dimensions or so, these are crucial for capturing long-range dependencies. They retain the global information, the big picture. And interestingly, these dimensions often show a persistent bias towards the initial sync tokens.
Sync tokens, what are those?
Yeah, sync tokens are kind of like mental anchors or stable reference points that the LLM uses.
Yeah.
They seem to help it maintain a grasp on the overall topic, no matter how long the conversation gets. They're often related to the very first tokens in the sequence.
Interesting. So lower dimensions for local chat, upper dimensions for the overall plot. That's a pretty compelling insight. How did the researchers actually test this idea, though? What empirical evidence did they gather to back up this bifurcation claim?
They did. And it's quite striking. First, okay, they visualized attention scores, and you could visually see these different patterns emerging. But the most definitive evidence, I think, came from their Gaussian noise experiments. They used a really demanding retrieval task called Needle-In-A-Haystack, or NIAH. This basically involves hiding a small piece of information, the needle, in a huge pile of text, the haystack, and seeing if the model can find it. They pushed this up to contexts of 32,000 tokens, which is pretty long.
Okay, so a real stress test.
Definitely. They started with a baseline where the model achieved perfect retrieval accuracy, 100%. Then they strategically added random noise like static to different sets of dimensions. When they added noise just to the first 70 dimensions, those supposed local context ones, the retrieval accuracy remained remarkably robust. It stayed over 97%, just a minimal drop.
So messing with the local context dimensions didn't really affect finding the long-range needle much.
Exactly. It confirmed their limited role in long-range dependency. But then, here's the kicker. When they added noise to the latter 58 dimensions, the ones they theorized were crucial for long-range info, the accuracy catastrophically plummeted.
How bad was it?
Down to an average of 53%, a massive drop. So this empirically validated their distinct, indispensable roles. It clearly showed these upper dimensions are vital for retaining that long-range information, while lower dimensions are specialized in encoding the local context. And this fundamental insight is precisely what drives FourierAttention's whole innovative approach.
Okay, that makes a lot of sense. So knowing that some dimensions care more about the big picture and others about the immediate context, how does FourierAttention use this insight to actually compress the KV cache in a smarter way, not just uniformly?
Right. This is where the HIPPO framework comes into the picture. HIPPO stands for high-order polynomial projections. It's a mathematically grounded approach for modeling long sequences. The idea is to approximate them with compact, finite states using orthogonal basis functions. Think of it like breaking down a complex sound into its simpler fundamental musical notes. These basis functions are those building blocks. It's designed to help retain the critical global patterns while filtering out redundant signals, allowing the model to focus on what truly matters over the long haul.
Okay, HIPPO provides the mathematical toolkit. But within HIPPO, why did they specifically choose Fourier transforms? They call it Fourier T over other options, like Legendre polynomials. What makes Fourier T the ideal choice here?
That's a crucial decision they made. They chose Fourier T, which stands for Translated Fourier Transform, over other bases like Legendre polynomials, leg-T, for a couple of key reasons. Fourier T uniquely exploits the shift invariance and temporal parallelism properties of Fourier transforms.
Shift invariance. Temporal parallelism. Can you unpack that a bit?
Sure. Shift invariance means it's really good at spotting patterns that repeat or shift over time, regardless of exactly when they occur in the sequence. This is perfect for text, where the same idea might appear at different points. And temporal parallelism means it can process different time steps efficiently, basically in a single pass. This fits beautifully with the token-wise parallel processing that happens inside transformers. It makes the computation very efficient. And beyond the theory, empirically, their ablation studies, which we can touch on later, consistently showed that Fourier T achieves lower reconstruction loss and better downstream performance compared to other choices like leg-T. So it just worked better in practice too.
That's really clever. So it's theoretically sound and practically efficient. Okay, so how does this online compression actually work then during the LLM's operation, both when it's first reading the prompt and then when it's generating new text?
Right, it operates in two distinct phases: the pre-filling phase and the decoding phase. So in the pre-filling phase, when the LLM first processes an input prompt, the initial few tokens, they use the first 4 specifically, and a certain number of recent local tokens, they set this window to 1024, are preserved completely. No compression on those.
Okay, keep the very beginning and the very recent stuff intact.
Exactly. Then for the other dimensions, specifically those long context-insensitive ones, the ones focusing mainly on local context, according to their bifurcation finding, these are identified and then projected onto these orthogonal Fourier bases. This effectively converts their temporal evolution, how they change over time, into a fixed length set of spectral coefficients. It's like getting a fingerprint of that dimension's history, but much more compact.
Yeah.
Oh, and they also handle converting the complex Fourier transform into a real-valued compression matrix, so it works with standard caches.
Got it. So that's setting things up. What happens during generation, the decoding phase?
Okay, so then in the decoding phase, as the model generates new tokens one by one, any tokens that fall outside that immediate local window of 1024 are individually compressed using this Fourier approach. The crucial step is that the compressed KV cache is then dynamically reconstructed or decompressed via an inverse Fourier transform right when the model needs it during the attention computation step. And to make this whole process compressing, decompressing lightning fast, and minimize the overhead of reading and writing data back and forth, they're developing a custom-built, highly optimized software component. Think of it as a super efficient engine part. It's called Flash FourierAttention. It's a custom Triton kernel designed to integrate the decompression directly into standard, already optimized operations like /attention2 and flash decoding, aiming for much better computational efficiency.
Right, because the decompression step itself could add latency if not handled carefully. Makes sense. And you also mentioned earlier a fine-grained compression schema. That sounds incredibly specific. Are they just compressing everything outside that local window, or is there a more clever strategy behind what gets compressed and where within the model?
Yes, that's another really neat part. This is where their asymmetric inverted pyramid compression pattern comes in, and it cleverly challenges some conventional assumptions. The rationale for this specific schema comes from their detailed observations of the statistical characteristics of the KV cache dimensions. Looking closely at the LLaMA models, they found two key things. First, the key cache consistently has a higher standard deviation, more variability than the value cache. Second, the upper layers of the model consistently have higher variability than the lower layers.
Okay, so K varies more than V, and upper layers vary more than lower layers. How does that translate into a compression strategy?
Well, based on this, their strategy is actually to compress more dimensions of the value cache and more dimensions in the lower layer caches to a fixed length, while retaining more of the key cache and more of the upper layer caches with less compression.
Huh, that's interesting. I think some other methods, like pyramid KV you mentioned, sometimes suggest preserving more in the lower layers. Why do they go the other way?
That's a great point. It seems counterintuitive at first, but FourierAttention's core criterion isn't just about attention scores or position, it's about reconstructibility from the compressed representation. The researchers found that the upper layer caches, even though they vary more overall, exhibit more complex, sort of oscillatory features. This seems to be because they're involved in more deterministic predictions further down the line. And these complex patterns mean they actually require more dimensions to be retained for stable output and accurate reconstruction of that essential long-range information. It's a very nuanced take based on the signal properties.
Wow, okay, that's quite specific. Do they give numbers on how much gets compressed where?
They do. In their experiments on the LLaMA models, overall about 76% of the KV cache dimensions ended up being compressed, but it was distributed very unevenly. For the first 4 layers, the lowest ones, they compressed 90% of the K dimensions and a whopping 95% of the V dimensions. But for the last 8 layers, the highest ones, they only compressed 50% of K and 70% of V. The mid layers were somewhere in between, around 80% for both K and V, so definitely an inverted pyramid shape.
That's really detailed. Okay, so this sounds powerful in theory and highly specific in its methodology, but how does FourierAttention actually hold up in the real world when put to the test against other methods?
Right, the proof is in the pudding, as they say. The authors rigorously evaluated FourierAttention on LLaMA 3.18b and LLaMA 3.23b models, and they compared it against leading KV cache optimization methods like Streaming LLM, SnapKV, PaLu, and CanVI. They used 2 primary benchmarks: LongBench, which is a suite that evaluates long context understanding across a variety of different tasks like summarization, question answering, coding. And the other was the Needle-In-A-Haystack, NIAH task we talked about earlier, specifically designed as a challenging retrieval test for finding embedded information in very long contexts. They pushed the context length up to 32,000 tokens in these tests. They also use multi-key, MK, and multi-value, MV variants of NIAH, which make the retrieval task even harder by adding multiple needles or making the context more distracting.
Okay, so a comprehensive evaluation setup, and what were the key results? Did Fourier-Attention really deliver on its promise?
It certainly seemed to. On LongBench, FourierAttention consistently achieved performance closest to the original uncompressed pre-trained models. Now, on the LLaMA 3.18b model, it was actually slightly inferior to SnapKV on average across the LongBench tasks, but it still showed remarkably strong overall performance, very close to the baseline. But where it really shone was on the challenging NIAH tasks. Here, Fourier-Attention consistently achieved performance closest to the original pre-trained models at that 32K context length. It generally outperformed all the other methods.
Even SnapKV, you mentioned that's theoretically suited for retrieval.
Yeah, even SnapKV showed some recall errors in these tough NIAH tests, whereas Fourier-Attention held up much better. And the other methods like PaLu and KIV, they saw pretty significant performance degradation at the higher compression ratios they tested, specifically at 75% compression. This suggests those methods really struggled with maintaining the long context capabilities under heavy compression, unlike Fourier-Attention, which seemed much better at preserving those critical dimensions due to its heterogeneous, frequency-based approach.
That's quite impressive, especially on the really long context retrieval. The ablation studies also offered some key insights into why Fourier-Attention works so well, didn't they? It wasn't just about the final results, but understanding the underlying mechanisms.
Yes, absolutely. The ablations were really informative. The first key insight came from confirming their choice of basis functions. Remember, they chose Fourier-T over leg-T. Well, they tested this directly. Under the HIPPO framework, Fourier-T consistently achieved lower reconstruction loss, meaning it could rebuild the original signal more accurately from the compressed form. And it also led to better downstream performance on the NIAH variants. This really reinforced their decision to use Fourier-T, highlighting its superior parallelizability and efficiency for this specific compression task.
Okay, so the Fourier choice was validated. What else?
The second big insight came from evaluating their compression schema. That asymmetric inverted pyramid schema we discussed, compressing more V-cache and lower layer caches. They compared it against other possibilities. A uniform compression scheme, a scheme that prioritized keeping K cache uniformly, and one that prioritized keeping upper layer caches uniformly. The proposed schema proves superior to all these alternatives. This highlights that frequency-based compression, like Fourier-Attention uses, has fundamentally different optimization characteristics compared to traditional token eviction methods. It really validates their approach of prioritizing reconstructability based on the signal's characteristics, not just, raw data size or simple heuristics.
And did they confirm which dimensions actually got compressed most?
They did. Finally, they analyzed the compressed dimension distribution. They looked at which dimensions ended up being compressed more frequently across the model. And the analysis showed that indeed in Fourier-Attention, the lower dimensions are more frequently compressed. Meanwhile, the upper dimensions, the ones critical for long-range information and forming those attention sinks we mentioned, they tend to preserve their complete temporal information more often, especially in the upper layers of the model. This directly supports their initial hypothesis about dimension bifurcation and shows how they successfully leveraged that understanding for efficient, targeted compression.
So it sounds like Fourier-Attention is a really significant step forward, offering not just performance gains, but some truly profound insights into LLM architecture itself. But, no new technology is ever perfect right out the gate. What are the current limitations the researchers acknowledge? Where do they see things going from here?
That's right, they're upfront about that. The primary limitation they highlight is that the custom Triton kernel, Fourier-Attention, is still under development. While it's designed to optimize memory access through streamlined read-write operations, by integrating the decompression directly into flash attention and flash decoding, its full computational efficiency compared to standard attention hasn't been completely achieved yet. It's a bit like having a powerful new engine design, but you're still fine-tuning the gearbox and the fuel injection system to get the absolute maximum performance and speed out of it. They are actively working on optimizing this kernel.
Okay, so the speed aspect is still being polished, and they're still aiming for even better performance overall, right? Trying to bridge any remaining gaps compared to the original models.
Precisely. They do acknowledge that a minor performance gap still exists compared to the original, fully uncompressed pre-trained models on some tasks. Further investigation into bridging this gap, getting even closer to that baseline performance while maintaining all the memory advantages, will be a core part of their future work. This kind of iterative refinement is pretty standard in advanced AI research.
Okay, so wrapping this up, what does all this mean for you, the listener?
Well, this deep dive into Fourier-Attention shows us, I think, a really fascinating path toward more efficient and yet still highly capable large language models. By understanding the truly heterogeneous roles, the different jobs of different dimensions within the transformer architecture, researchers can be incredibly precise about what information to keep and what information can be effectively compressed. And this leads to models that can potentially handle massive context lengths without completely breaking the bank on memory requirements. Yeah, and this ability to sustain long context understanding in LLMs while significantly reducing their memory footprint could genuinely unlock entirely new applications. It could make these powerful tools much more accessible, perhaps running effectively in more constrained environments like on-edge devices or personal computers. It really pushes the boundaries of what's possible with current hardware. And it opens up new avenues for on-device AI, potentially bringing these advanced capabilities much closer to everyday use cases.
It really makes you think about the hidden complexities humming away inside these models, doesn't it? That a relatively simple mathematical tool like Fourier transforms, when combined with a really deep understanding of how attention works at such a granular dimensional level, can yield such profound gains in efficiency.
Absolutely. It's a testament to digging deeper than the surface level.
So maybe for you, the next time you interact with an LLM, especially if you're giving it a long document or having a long chat, perhaps ask yourself, which parts of its memory are truly essential for understanding this, and which parts perhaps could be beautifully and efficiently approximated by a Fourier series?